Next speaker is Abdelrahman, I think. So the talk starter is Hydrogen in Aviation and Propulsion Research at Cranfield University. Again, you have less than 30 minutes, and then we'll have questions and answers.
Hello, good afternoon, everyone. First and foremost, I'd like to thank Jimmy Turner for the kind invitation. I'd like to thank the rest of the CCRC for the fantastic organization, and Bassam for moderating this session. It always feels good to be back at Saudi Arabia. I was born here some 40 years ago. My eldest daughter was born here like 15 years ago. Lots of lovely memories in this country, and I wish you all the best. As Bassam introduced, I'll talk about the hydrogen in aviation and propulsion research in Cranfield University. This is my first visit to KAUST, so the presentation would be likely high level. I'll talk a bit about piece of every piece, really, and hopefully we will dive deeply into the technical things in my next invitation, I hope so. Let's get to the bottom end of it. Cranfield University, if you consider the topic of hydrogen, could be looked at one-stop shop, basically. So we do everything when it comes to hydrogen, not necessarily only the end use, but we start with things like fuel production, for example, all the way through until end use, passing by supply chain, fuel systems, hydrogen in liquid and gaseous forms in combustion for reciprocating engines, as well as gas turbines. And also, we do work related to policies, economic, and management legislations as well. I am part of the Center of Thermal Power and Propulsion, or Propulsion and Thermal Power Engineering. This center is dated back as early as 1950, just after the Second World War. The building we are based in is called Whittle Building. It's named after Frank Whittle, the person who invented the gas turbine. So lots of rich history. We are about 65 academics, 20 visiting academics from industry. We have 5 world-class groups within our centers. Each one of them is doing their own bit. 150 PhD and master students. We are postgraduate university only. So like KAUST, we don't have undergrads. We have industrial scale experimental facilities. We do bespoke courses for everything really related to power and propulsion, different applications. I'll come to this late in my presentation. We house one of Rolls-Royce UTCs in England. We have Cranfield Air and Space Propulsion Institute, CAPSI, and CRANSIDS, also under our umbrella. And those are some of our partners that we are proud to be working with from main engine manufacturers, airlines, airframers, airports, OEM manufacturers as well. We do, when it comes to propulsion and thermal power, we do all the range for land, air, marine, and aerospace application. So it's not necessarily we are focusing only on the aerospace, but we do all sides of things. We start from the isolated power plants all the way through up to the fully advanced aircraft design and all of these kind of things. We have diverse range of projects. Those are a few examples of the topic we talk about when it comes to research fellows and PhD works. These are with the dotted line, with the red dotted line, these are the experimental work we can do, again, diverse range. And obviously, you can see with the timeline increasing, the degree of advancement is obviously increasing with time as well. These green areas are the work supported by the ARC, which is the Aerospace Integration Research Center. It's a monster that is basically sponsored by Airbus and Rolls-Royce as well. So we try to bring the titans together. These are some of the areas. And we are very keen to have our master students working on the very high end of things when it comes to development. So we try always to have the individual research projects for our master students involving with every bit we do, really. We start all the way through from TRLs 1 up to 6. So from the very first point up to almost, sorry. We have industry scale experimental facilities. So we have cabin blower rig. We have high pressure, high temperature combustion rig. We have subsonic atmospheric altitude facility, PIV research rig for advanced intake systems. We have high-speed drivetrain facility, supercritical CO2 facility. We also focus on modeling, obviously, different softwares. We have ANSYS Fluid. We have Siemens Star CCM Plus for different modeling. And we develop our very own in-house modeling tool that I'll mention briefly later in the talk. That can do everything when it comes to gas performance prediction and everything related to the air vehicle, basically. About the hydrogen for civil aviation and propulsion system, Cranfield University, as I said, from 1950s, have demonstrated leadership in that. There are few aspects of this when I say leadership. So we have Cranfield Hydrogen Integration Incubator, March this year, so 6 weeks. We have received the largest ever funding, basically 69 million from UK RPIF, which is Research Partnership Investment Fund, and industry partners as well. This investment, the huge investment, is a step change by developing the first largest scale research hub at any UK airport. And this is one of the things. We have an airport at the university. Our students got in the master level as part of their study to go to the airplane and take actual engine measurements for thrust and performance and all of these kind of things. So we are hoping to unlock lots of challenging when it comes to upscaling of the hydrogen use. Bottom left, this is the new facility that we are currently working on, or literally starting, Hydrogen Integration Research Center. This map shows where the proposed development when it comes to application of liquid and gaseous fuel systems as well here, enabling Jet Zero investment also in our global research airport, which I just mentioned. Also, another aspect of the partnership is our APSRC, Central for Doctoral Training, CDT, and this unique thing about it, it's only about net zero aviation. So collaboration with Cardiff University, Strathclyde, and National Center for Aerospace Science. We look at different things throughout wide spectrum related to zero emissions technologies, electrification, SAF, hydrogen, ultra-efficient aircraft propulsion system, life cycle, operation, everything, commercialization, social aspects as well. And for the CDT, it's not the standard PhD program, but rather it's a program where students get to study for 5 years. In UK, it's usually 4 years, 3 years for your PhD, and 1 year for writing up. We have the first year, the students get to be taught about different things, so they take professional development courses on things even related to management and stuff like that. This is some of the projects we have been working on over the years, over the past quarter century, basically. Covers everything: combustion, emissions, engine integration, efficiency, all of that, SAF, gaseous hydrogen, liquid hydrogen. Some of these names might be familiar to Rod and to Jamie in particular, but long story short, you can see the key to the right, to the left of the screen. We cover different aspects when it comes to research. So there are researches related to hydrogen, researches looking after NOx, research is aiming at integration of alternative fuels such as SAF and these kind of things. And aerospace integration in general. I'll mention a couple of them when I talk about our research in my group. So this is the low emissions technologies and combustion group that I belong to, one of 5 groups in the center. I'll just mention a couple of projects this one is very recent, it just ended recently. Enable H2. Mid-bottom is the consortium of the project. And obviously, we were proud to be advised by this elite list of industry partners. So it's a Horizon 2020 project, 4 million euro fund, and a few work packages, as you can see. So there is a fuel system heat management package and the hydrogen micro-mixer combustion. This was the work package that Cranfield was involved in. This will tie very nicely with what Rod has mentioned in his presentation. But long story short, the aspects is to basically enable technologies for hydrogen combustion, liquid hydrogen, basically. So we use a hydrogen micromixer for ultra-low NOx, fuel system heat management, and this was the part done by Chalmers University in Sweden. And we also have techno-economic environmental risk assessment as well as part of the project. So we said two words, hydrogen and micromixer. So when we say hydrogen micromixer, we need to justify why hydrogen and why micromixer, basically. So the case of liquid hydrogen as a civil aviation fuel stands out for itself, especially, and this is important in the long run. First and foremost, without a shadow of a doubt, emissions is always better when it comes to that. You can see green line for liquid hydrogen means it's superior relative to other fuels, including LNG as well, and other drop-in replacements. When it comes to cost, yes, at the moment, it's quite expensive relative to standard fuels, even relative to SAF, but hopefully the numbers mentioned here is 2050. I think the pace is better at the moment, and potentially this would be realized sooner than that. Risk and safety, obviously, it's all risky, regardless of you are combusting something massively. So, but long story short, you can see how many greens here we have for liquid hydrogen relative to the rest of the fuels. So it sits out the case from a combustion stance. Obviously, hydrogen is a carbon-free fuel. So there is no carbon dioxide, carbon monoxide, unburned hydrocarbon. So anything has to do anything with carbon is not there. Consequently, you have less luminous radiation because there is no soot, basically. So this will give a better life and better durability for the combustor liner. Also, because hydrogen has an extraordinary combustion characteristics, this means because of the wider flammability limit and the very high flame speed as well, you can actually find out that the control range for hydrogen when it comes to equivalence ratio is way leaner than kerosene. So you are moving between 0.15 up to 0.6 more or less relative to around the stoichiometric conditions when it comes to kerosene. And that's why with this lean combustion, we will have lower thermal NOx and also shorter combustion, so more efficient basically. I'll fly quickly over this. This comes more or less in representation. So this is the micromixer. Why micromixer? Again, we would like to reduce NOx. So one aspect is to use hydrogen. The other is the micromixer. So by using these, the mixing length is minimized and the mixing intensity maximized. So here, this is the standard mixer. So you will have like this tube here where your hydrogen or your fuel basically is coming from. This is the conventional one. Your air is coming like this. You mix here, you end up with something like this, and we all know what the yellow flame presents basically. For micromixer, this is what it looks like. So there is a photograph in the next slide, but these holes here, these lines, perpendicular to the plane of the screen, basically, to the plan of the screen, is where the air comes from. The fuel is coming from a very little hole here. So these on the perpendicular direction, basically. So you have your air coming from here, you have your fuel coming from here. So down and up, basically. Down in the top one, middle one, you will have two of them, and lower one, you will have one up as well. And because of this micro-mixing, we have a very reduced risk for flashback. There is no rich pockets, which is quite important. So anything around phi equal 1 doesn't exist. And that's why it can provide the ultra-low NOx. This is the experimental setup. So we have a pebble bed air heater, combustion test bed. It can go as high as 1700 K, 15 bar. This is the maximum. The points we tested in the project was around 10 bar, 9 bar-ish. We have 4 kilogram per second air mass flow rate to lift, top lift. This is the rig itself. This is an overlay out of the layout of the test rig itself. This is the optical window, and here, these very little holes perpendicular to the screens are the supply for the hydrogen fuel, or the fuel, and these are for the air. It's a 3D printed plates with micro EDM manufacturing, sorry, hole diameter 0.3 millimeters. So that's why micro mixing was possible. Another project which we are kicking started at the moment when it comes to experimental work, it's underway for a year or something. Again, our prestigious consortium here to the right of the screen, Project Minimal, it's a Horizon 2020 project as well. And it looks basically at new propulsion systems fueled by either hydrogen or SAF using a composite cycle engine. These are the benefits here. But long story short, we are expecting to achieve from the combustion, from the power unit itself, 15% improvement in thermal efficiency and reduction in the core weight by 30%. And because you will have now less weight of the vehicle, you will end up having an improved, further improved in the specific consumption, so 22%. And this is the impact it will have eventually, 60% reduction, 2/3 per passenger, relative to using conventional fuel relative to the standard engines, and 90% if we use SAF or hydrogen. Again, the project basically has two legs. So you have work package 2, the NOx reduction, 3, thermal management, like the same way we had it before. We will be in Cranfield looking after this, at Chalmers University, Sweden, looking after that, and the whole system integration is ours. Those are the targets. We didn't start, obviously, yet, but these are the targets. 80% reduction from contrails, more than 50% net NOx, and more than 1/3 fuel reduction, and 1/3 up to 100% carbon dioxide reduction, depending on the source of fuel you are going to use. So very briefly, I'll fly over this one. There are 3 concepts when it comes to composite cycle engines. The first one is the baseline CCE, which relies basically in a standard reciprocation internal combustion engine. I've been working in engines for 15 years, so I love them. I can't live without them. And I hope they stay around for basically my lifetime. But long story short, so rather than having the standard compressor turbine as power source, you will have your compressor here, right? And there is intercooler in the middle. And then in this baseline, there were 2 V10 4-stroke engines. So you have a V engine, 10 cylinders, 2 of them. And then you use the air coming out, you run the engine as usual, you get your exhaust to drive the turbine, which is downstream here, basically. This is the baseline. It moved then from this proposal to the free double piston. So basically you have a combustion chamber here and there, and then you have your piston, linear engine basically, but without a power generation function. What we will be testing here is opposed free piston. So basically you have a combustion chamber, central combustion chamber in the middle, and these are your 2 pistons. Here you have an air spring, so your piston can come back when the cycle happens. And these are linear generators, electromagnetic generators, and they are expected to achieve this 15% we have mentioned about the improvement in thermal efficiency, basically. These are modular, or the plan for them is to be modular, so you can have them in an annulus shape, basically, and this would be your power unit, basically. So yes, finally, I'll go to my other hat. I'm proudly the director of the master course for thermal power and propulsion. So one of the things I'd like to encourage undergraduate students and people from different organizations to have a look at this course. It's 1-year program. We have 2 intakes per year. At the moment, as we said, we work on aerospace, air, marine, and land applications as well. So we had 5 programs, but we will be combining them starting from the next year, 2025, to be 2 measures. The first measure is for aerospace propulsion, and the others for land and marine power. This is the course structure. As I said, it evolves around thermal power and propulsion, starting or looking at things on the individual levels like combustors, engine systems and all of these kind of things, all the way through until full system integration. We have our very own in-house developed modeling software that can model and predict the engine performance and do simulation for everything really, not just for the turbine, but for the whole system together. This is our structure. We have 100 credit taught modules, 100 credit as research project. And that's why I said it's quite important that we align the master students to all the projects we are working on. Finally, I do understand it's quite very short notice, but for the people interested in the hydrogen, we have a short course. As I said, we have more than 20 short courses bespoke for the people in the industry. This is a short course for hydrogen for civil aviation. It starts next week, 20th. It's 4-day, and we host lots of people from Rolls-Royce, reaction engines, industry, IATA, even legislation's body as well, to talk on that. Very good, very good. I'd highly recommend it. If you didn't manage to enroll because of the short time, there is a little version of it running on Toulouse, France, October time. But next year, same time, hopefully we'll run our main course in Cranfield. And yeah, and that's it for me. Thank you so much.
Thank you very much for the talk. We have good time for questions, please. If you have any questions, raise your hand. Okay. Maybe while I'm bringing, I have a question about reciprocating engines. One, how do you cool those? And isn't it too heavy to be up in the air?
Yes, and that's why for the baseline testing, we are not doing this experimentally at Cranfield. And this is the reason why we decided to move basically from them to the free piston engine, because obviously with free piston, you get rid of the crank and also the offset in the engine, all of these kind of things. So it becomes more light. The thing is, these type of engines are still in the R&D phase, basically. They have run before using spark ignition fuel, but it will be in Cranfield where we will be testing it on hydrogen.
All right, so you mentioned that there is a software for measuring performance, engine performance. So do you allow your students to use it post-graduation?
Absolutely, and this would be part of their master individual research project if they decided to. So for the 100 credit of taught courses, they got taught, and then they have their other 100 credit where they got to choose their own research project. If they decided they would like to run engine simulations using our softwares, this is their project, and it's half of the degree already.
Other questions?
Thanks. Very interesting. Thank you very much. As someone who's spent their life obsessed with internal combustion engines, I can hardly believe I'm about to say this. But one of the real advantages of the gas turbine to me, and the reason why it's become the device that it has become, is that it did away with reciprocation and all the parts in piston engines. Now, the old piston aero engines were absolutely fantastic, but the step change was moving to pure rotational motion, reducing a load of parts, continuous combustion, and then you've got a pathway to the fantastic durability that we have at the moment. Now, I get the whole reason. I know all about the Bauhaus studies, and because you put some of those up there, and I've seen some of the stuff with the free piston engines and all that stuff, and it's brilliant from an engineering point of view. But it's terrifying from a passenger point of view, in my opinion. I've been in piston-powered aircraft before, and as someone involved in engines, you just think, oh, I really hope nothing breaks. Whereas it doesn't even cross your mind with a gas turbine. So you're looking at a lot of interesting things there, and one of the things that always comes to my mind when you're doing liquid hydrogen, someone has invested a lot of energy liquefying it, physical energy. And if you're just going to vaporize it, just put a bit of heat in and vaporize it, and then you're going to put it into the engine gaseously, you are throwing away a load of energy that has been put on board the aircraft in a physical form. So in these advanced cycles, have you ever thought about digging out again the Ray expander cycle? So it's no longer a dual cycle, Brayton cycle if you must. It's no longer a dual cycle. It's more like a steam cycle. It's a phase change cycle. Are you going to consider looking at anything?
Thank you for the very comprehensive question. It's a bit early day. It's a bit early days for us to see. Yourself obviously know more than many people. It takes time to set the rig and make sure that everything works in place. But we will be certainly looking at some of these aspects. By the way, coming back to the reciprocating engines, it never broke down with Indiana Jones, did it? So if it doesn't break with Indiana Jones, it's not going to break with us. Anyway, so the point to make here about liquid hydrogen and how people like spend lots of energy to liquefy it and then we do it this way, I'm looking at it from the perspective of liquid hydrogen as an energy carrier, basically. It has to be liquefied so we can carry out energy on board. And this is what matters because eventually it's 120, 130 megajoule per kilogram. So I need to have it this way. Combustion stance, way or another, it will have to go this way. Even you are talking about SAF or kerosene, as liquid, it has to go through this way. But yes, certainly, we are hoping to dig behind lots of things. It's a new era. It's a new territory for lots of partners in the project anyway. But yeah, we'll see what we can do. Thank you.
Thank you, Professor, for the presentation. My question is, we're just discussing this, me and my colleague over lunch. The technology of hydrogen fuels seems to be stuck for, let's say, the few last decades. So what do you think is the kind of breakthrough do you need in the hydrogen fuel technology that would take it, let's say, beyond this stage that it's in right now? Because it seems it's a little bit analogous to, for example, the solar energy technology. It's kind of stuck. It's not really gaining any momentum over the years. What do you think is the kind of breakthrough does it need?
Fantastic. Thank you so much. It's a very interesting question. So there are a couple of things from my own perspective about that. First and foremost is the hydrogen production itself. So people are talking about hydrogen as a clean fuel, which would be, if it's green, basically coming from renewable electricity and electrolysis, basically. So you need renewable electricity, and this doesn't cover much. Green hydrogen production relative to the total production is less than 1%. So 99% of your hydrogen comes from dirty sources, if I may say, whether it's gray coming from like steam reforming of methane, or black coming from coal gasification like in China. Yes, carbon capture would convert either the gray or black to blue, and I think Saudi Arabia is doing great work on that, on the blue hydrogen. But the cost is one thing. Eventually, if you talk about customers, whether these are people like us driving their cars around, or airframers or people, airlines, companies, it's cost. If you increase the fuel cost, this means people will pay more. So your product will be less viable. Lots of people will just opt for the cheaper one. Number one. Number two, the infrastructure as well. And that's why this will tie nicely, actually, thank you for this point, to what we are doing in Cranfield, because we do the production and we do the supply chain as well and management. So production is another thing. Transport is another thing. And third is the energy content, which is problematic for hydrogen as gas. Because the problem is when you talk about movable applications, whether it's airborne, like in airplanes, or in land transport, long story short, you have tank. And this tank is for fixed volume. So you have 70-liter tank, or you have 150-liter tank. How much mass, because the calorific value of fuel is mass basis, is kilojoule per kilogram. How much kilograms you would need to put in there will obviously determine how much energy you can carry around in a certain volume. That's why some people are looking at ammonia as an energy carrier for hydrogen, because it's 1/7 cheaper to move ammonia around than hydrogen. especially for hydrogen. If you use it at 175 bar, 175, which is the standard pressure for the bottles, very little. You can go up to 350, still little comparable to others, 700, the very big tube trailers, until the liquid hydrogen. And this is this is the bottleneck, if I may say. It takes lots of energy to produce liquid hydrogen, and you need to revert it back at some point again. And cryogenics of hydrogen is very challenging. I did some work with Rolls on the liquid hydrogens. It's 4K, 4 degree K. So this is minus whatever, 270, 269. Yeah. So until we crack on with all of this, your question will be hanging around.
Please join me in thanking Abdelrahman again.